Hello everyone. In the last lecture we have seen the properties of Z transform. In this lecture we are going to obtain Z transform of some standard functions. Consider the first function, which is unit impulse function, which is defined as delta of n is equal to 1 for n equal to 0 and 0 for n not equal to 0, means otherwise. So its graph is like this. For n equal to 0 only, delta n is equal to 1, and for remaining n from minus infinity to open 0 and open 0 to infinity, it is 0. By definition of Z transform, we can get Z transform of delta n is equal to summation from n equal to minus infinity to infinity delta n z raised to minus n. Now put the values of n one by one. That will give us dot 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 plus. If we put n equal to minus 2, it will give us delta minus 2 z minus of 2 z square plus delta minus 1 z of minus 1 is 1 plus delta 0 z raised to 0. Put n equal to 1, delta 1 into z raised to minus 1 plus delta 2 z raised to minus 2 for n equal to 2 plus so on. Now from the given function, replace the values of delta minus 2, delta minus 1, delta 0, delta 1, delta 2 and so on from on both the sides, left hand side as well as right hand side of this expression. So delta n is 0 for all values except n is equal to 0, that is delta 0 equal to 1, remaining all delta values are 0. Therefore we will be getting our expression as dot 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 plus 0 into z square plus 0 into z raised to 1 plus 1, z raised to 0 is 1 only, plus 0 into z inverse plus 0 into z raised to minus 2 plus so on. So that will give us f of z equal to 1. This is the required z transform of the unit impulse function delta n. Second standard function is unit step function, which is given by u of n is equal to 1 for n positive, non-negative, n greater equal 0 and 0 for n negative, whose graph is like this. So 0 for n negative and it is 1 for n positive. So that is the unit step function. So Z transform is given by Z of un is equal to summation from n equal to minus infinity to infinity u of n z raised to minus n. Now u of n is 0 for n less than 0 and it is 1 for n greater equal 0. So we will put the values directly and we will get dot 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 plus 0 into z square plus 0 into z raised to 1. So these all they are terms corresponding to negative n, then plus. Now the remaining terms, they are the terms corresponding to n greater equal 0, that is n non-negative. So for n equal to 0, we will be getting 1 into z raised to 0 plus 1 into z raised to minus 1 plus 1 into z raised to minus 2 plus so on. So we left with 1 plus 1 upon z plus 1 upon z square plus so on. So this is in geometric progression with common ratio 1 upon z, and hence the summation will be given by first term, which is 1 divided by 1 minus the common ratio, which is 1 upon z, and this is true for mod 1 upon z less than 1. Simplify this expression, we will be getting f of z equal to z upon z minus 1 for mod z greater than 1, which is the required z transform for the unit step function. Next function is, or the sequence whose general term is is f of n is equal to a raised to n for n greater equal 0 and a any scalar. So the z transform is given by z transform of sequence f of n is equal to summation, as we have been given n greater equal 0, so our summation runs from 0 to infinity over n, a raised to n, z raised to minus n, because our f of n is a raised to n. Now put the value of n one by one. For n equal to 0, we will be getting the term a raised to 0, z raised to 0. For n equal to 1, it is a raised to 1, z inverse, plus for n equal to 2, a square z raised to minus 2, plus so on. Simplify this expression, it will give us 1 plus a upon z plus a square upon z square plus so on, which is again in GP with common ratio a upon z, and hence this infinite sum is given by first term divided by 1 minus common ratio, that is 1 upon 1 minus a upon z, which is true for mod of a upon z strictly less than 1. Simplify this expression, we will get f of z equal to z upon z minus a for mod z greater than mod a, which is the required z transform for the sequence f of n whose general term is f of n equal to a raised to n. Next standard function is the sequence whose general term is f of n is equal to a raised to n for n strictly less than 0 and a is any scalar. So by definition of Z transform, we will be having Z transform of f of n is equal to summation from n equal to minus infinity to minus 1 a raised to n z raised to minus n. Now here we will put the values of n starting from minus 1. So that will give us a raised to minus 1z plus a raised to minus 2z square plus a raised to minus 3z cube plus so on. Simplifying it, we will be getting z upon a plus z square upon a square plus z cube upon a cube plus so on. Again, which is in GP with common ratio z upon a and first term z upon a. Therefore, the sum is given by z upon a divided by, that is the first term divided by 1 minus common ratio. So z upon a divided by 1 minus z upon a for z upon a strictly less than 1. Simplifying this expression, we will be getting f of z is equal to z upon a minus z for mod z less than mod a, which is the required Z transform for the sequence f of n is equal to a raised to n for n strictly less than 0. Next standard function is sequence f of n whose general term is a raised to mod n for all n and for any scalar a. Then its Z transform is given by how we have obtained Z transform in last two sequences. Same procedure we follow here, and we will be getting Z transform as f of z equal to az upon 1 minus az plus z upon z minus a for mod a strictly less than mod z strictly less than 1 upon mod a. So this is the Z transform for the sequence f of n equal to a raised to mod of n. Next standard function is f of n is equal to cos of alpha n for n greater equal 0 and alpha is any scalar. So that will give us, by the definition of Z transform, we will be getting Z transform of f of n is equal to summation n equal to 0 to infinity. Our f of n is cos of alpha n z raised to minus n. For the simplification purpose, we replace this cosine term by its exponential equivalent using Euler's formula. So that will give us summation n equal to 0 to infinity e raised to I alpha n plus e raised to minus I alpha n upon 2 z raised to minus n. Take 1 by 2 common, and under the summation sign we will multiply by z raised to minus n inside the bracket, and that two terms will be expressed as e raised to I alpha z raised to minus 1 bracket raised to n plus e raised to minus I alpha into z inverse bracket raised to n. Now both these are geometric progressions, wherein first one is the GP with common ratio e raised to I alpha z inverse and the first term 1, and second one is in GP with common ratio e raised to minus I alpha Z inverse with first term as 1. Therefore, the infinite sum in both the geometric progressions will be given by 1 by 2, 1 upon 1 minus common ratio, that is 1 minus e raised to I alpha Z inverse plus 1 upon 1 minus e raised to minus I alpha Z inverse, which is true for first one is true for mod of e raised to I alpha Z inverse strictly less than mod 1, and second one is true for mod of e raised to minus I alpha Z inverse strictly less than mod 1. Now we will perform the cross multiplication that will gives us like this simple cross multiplication, and simplifying this expression we will take this Z inverse on the right hand side. So this expression it will becomes mod of e raised to I alpha strictly less than mod Z, and mod of e raised to minus I alpha strictly less than mod Z. We know that mod of e raised to I alpha and mod of e raised to minus I alpha is equal to 1. So in the further simplification we will be getting an expression which is 1 by 2 into 2 minus e raised to I alpha plus e raised to minus I alpha into Z inverse divided by 1 minus e raised to I alpha into Z inverse minus e raised to minus I alpha Z inverse plus Z raised to minus 2, which is true for mod Z greater than 1 for both the terms. Now, using Euler's formula, we are going to replace this e raised to I alpha plus e raised to minus I alpha both in numerator as well as in denominator by 2 cos alpha. Therefore, we will be getting a further expression as 1 by 2 into 2 minus 2 cos alpha into Z inverse divided by 1 minus 2 cos alpha into Z inverse plus Z raised to minus 2. True for mod Z greater than 1. Now this 2 will get cancelled from numerator and denominator, and we are going to multiply both numerator and denominator by z square. So that will gives us z transform for the sequence cos of alpha n for n greater equal 0 as f of z equal to z into z minus cos alpha divided by z square minus 2z cos alpha plus 1, for which region of convergence is mod z greater than 1. So this is the required Z transform. In same way, we can obtain Z transform for the next sequence whose general term is sin alpha n for n greater equal 0, where alpha is scalar. So Z transform is given by Z into sin alpha divided by Z square minus 2Z cos alpha plus 1 for mod Z greater than 1, which is the region of convergence. Z transform of the sequence f of n equal to cosine hyperbolic of alpha n for n greater than or equal to 0 is given by f of z equal to. So it is similar to trigonometric cosine function, just replace that cosine function by cos hyperbolic. So f of z is equal to z into z minus cos h alpha divided by z square minus 2z cos h alpha plus 1, where region of convergence is mod z strictly greater than maximum of mod of e raised to alpha or mod of e raised to minus alpha. Z transform of the sequence whose general term is f of n equal to sin hyperbolic of alpha n for n greater than or equal to 0 is given by f of z equal to z into sin h alpha divided by z square minus 2z cos h alpha plus 1 for mod z strictly greater than maximum of mod of e raised to alpha or mod of e raised to minus alpha. Next function is or sequence is f of n is equal to, this is the combination mcn for n less than or equal to m, and which is non-negative. So use the definition now. So here we will note down one thing, that combination mcn is equal to 0 if n is strictly greater than m. So by definition of Z transform of f of n is equal to summation n equal to 0 to infinity mcn z raised to minus n, which is equal to mc0 plus, now we are replacing the value of n one by one, so mc0 plus mc1 z inverse plus mc2 z raised to minus 2 plus so on plus mcm z raised to minus m plus, when n is greater than m, then mcn is 0. That already we have noted. So the remaining terms will be 0. So this expression is nothing but the binomial expansion for 1 plus z inverse raised to m. Therefore, z transform of MCN, that is f of z, is equal to 1 plus z inverse raised to m for mod z strictly greater than 0. So region of convergence is mod z strictly greater than 0. Next function is f of n is equal to NCM for n greater equal m. So in same way we can follow the procedure that will gives us z transform as f of z is equal to z raised to minus m into 1 minus z inverse raised to minus m plus 1 for mod z greater than 1. Next one is the sequence whose general term is f of n is equal to m plus n cm for m greater equal 0, whose z transform is given by f of z is equal to 1 minus z inverse raised to minus m plus 1 for mod z greater than 1, which is the region of convergence. Last sequence is f of n is equal to m plus n cm a raised to n for m greater equal 0, whose z transform is given by f of z is equal to 1 minus az inverse bracket raised to minus into bracket n plus 1, and region of convergence is mod z greater than mod a. So this result is important in view of inverse z transform. There are some deductions to this result, which are: for m equal to 1, z transform of n plus 1 a raised to n is equal to z square upon z minus a bracket square. For m equal to 2, it is z transform of n plus 1 into n plus 2 divided by 2 factorial a raised to n is equal to z cube upon z minus a bracket cube. And for m equal to m minus 1, z transform of n plus 1 into n plus 2 so on, n plus m minus 1 divided by m minus 1 factorial into a raised to n is equal to z raised to m divided by z minus a raised to m for mod z greater than mod a. So these are z transform of some standard functions. I hope you understood this. In the next lecture, we are going to solve the problems on z transform. Thanks for watching this video.